welcome to the debate. Today, we are diving into one of the most critical factors that influences data transfer in modern high bandwidth networks, and that's the efficiency and maybe more importantly, the resilience of TCP congestion control algorithms. As we push towards 100 gigabit links, even faster, the old rules, well, they seem to be breaking down.
That's right. The big three challenges, latency, which is round-trip time or RTT, packet loss, and buffer or window size, they're more tangled up than ever. And there's this empirical finding that really drives our discussion today, and it's pretty stark. Even like tiny amounts of network instability, say just 1% packet loss, can cause absolutely catastrophic drops in throughput. We're talking, 70% reduction, sometimes even more.
Exactly. So the question before us is, well, can cubic TCP, which is the current default congestion control algorithm practically everywhere, can it really handle this modern fragility? Or does the newer model-based BBR algorithm warrant, immediate and universal adoption because it's proven to be, frankly, much more resilient? I'm going to argue that the empirical evidence we have showing BBR's ability to maintain high throughput, even when there's significant packet loss, it basically makes cubic obsolete for today's internet standards. The data, I think, clearly supports making a shift.
And I come at it from a slightly different angle. While BBR certainly posts some impressive speed numbers, especially in specific controlled tests, I'm going to argue that Cubic's established characteristics, things like its fairness, its stability, its very predictable sort of democratic response to congestion, these make it necessary to keep Cubic as the universally deployed baseline default. We really can't sacrifice broad network equilibrium just for localized, sometimes aggressive speed gains.
Okay, I see why you'd emphasize stability, but let me give you a different perspective, one that's maybe rooted more in the, let's call it the physics of modern networks. Cubic's reliance on packet loss as the primary signal for congestion, well, that seems fundamentally flawed in today's high-speed, high-latency environments. We often call these long, fat networks, or LFNs, those paths where the combination of huge bandwidth and long delay makes every single lost packet incredibly costly. And Cubic's reliance on loss leads directly to those catastrophic throughput drops we've measured when, inevitably, some loss occurs. The data makes this flaw, I think, painfully clear. If you look at a controlled 1 gigabit per second test scenario, right, introduce just 1% packet loss, Cubic's performance just collapses. Its throughput went down by a staggering 70.7%, fell from over 800 megabits per second down to just 235 Mbps. Now, that isn't just slow performance, that's systemic fragility baked right into the core protocol.
Okay.
In the exact same scenario, BBR, which uses a completely different approach, a model-based one estimating available bandwidth in minimum RTT, it only saw an 8.5% decrease. It kept performance close to 800 Mbps. That disparity, a 70% collapse versus just minor degradation, that's the entire argument for BBR right there.
That's an interesting point. And yeah, the raw speed metric is undeniably powerful. Though I would frame it a bit differently. Cubic became the default choice across, everything Linux, Mac OS, Windows. It's been the foundational algorithm since the mid-2000s, right? And there's a reason for that, a reason that goes beyond just raw speed. It prioritizes fairness and stability. Its systematic design ensures proven reliability as a universal algorithm. It has to serve flows ranging from your local data center link all the way to a transcontinental one.
Right.
And the key here, I think, is Cubic's RTT independence in its window growth. Unlike older TCP algorithms, Cubic's aggressiveness isn't tied to the round-trip time of the flow. This RTT fairness is absolutely essential in modern infrastructure. Think CDNs, where flows might have wildly different latencies. You could have a 5-millisecond flow competing with a 100-millisecond flow. And studies show Cubic achieves, 3 to 5 times better fairness compared to older loss-based algorithms like Reno in these mixed RTT situations. Cubic's measured window function, the concave, plateau, then convex probing, It's designed to be more like a patient traffic light system. It lets the network stabilize before it rapidly probes for more capacity, and that stability is critical.
But that measured approach you describe, that translates directly into the throughput penalty we just talked about. A 70% collapse because of a 1% glitch? That sounds like fragility to me, not reliable performance. You mentioned long, fat networks. Well, the Mathis equation mathematically established decades ago just how devastating packet loss probability P is to TCP throughput. And when latency goes up, the control loop for TCP recovery just gets longer and longer. Cubic gets stuck in this slow recovery mode for extended periods on LFNs because it has to wait for that lost packet signal, and then it has to methodically back off and restart. It just seems perpetually ill-suited for the internet we actually use today.
I'm not entirely convinced by that line of reasoning, because Cubic's sharp multiplicative reduction when it detects loss, that's the foundational principle of additive increase multiplicative decrease, AIMD. It is the mechanism that prevents chaotic congestion. You're calling it fragility, but I'd call it responsible network behavior. The key difference is the signal. Cubic assumes loss means congestion, and that's generally a safe, conservative assumption for the network as a whole.
But is it always congestion?
Well, perhaps not always, but if BBR avoids interpreting all losses as a sign of genuine network congestion, and you're right, sometimes loss is just random buffer overflow or corruption, not necessarily full link saturation, then it raises a significant risk. A risk of contributing to chronic buffer bloat and excessive queuing latency. And queuing latency is a major killer of user experience, especially in these high-speed environments where, frankly, router or switch buffers might not be adequately scaled for the sheer volume of, say, 100 gigabit Ethernet traffic. Cubic manages congestion signals predictably. It keeps the network responsive by quickly backing off when it sees trouble.
Okay, I have to push back on that premise, though, especially the idea that BBR risks buffer bloat more than Cubic. Think about it. Cubic, by its very design, must fill the buffer until the router starts dropping packets. That's how it signals congestion. It relies on inducing buffer bloat to figure out the path capacity. That is, sort of, the definition of creating high queuing latency. BBR, however, it operates on an entirely different principle. It acts more like a road surveyor. It's constantly measuring the actual available bandwidth and the minimum RTT. Its fundamental goal is low latency operation by keeping queues shallow, positioning the sending rate right at the bottleneck capacity, but crucially not pushing past it. It doesn't need to induce packet loss to understand the network's limits. So arguably, BBR is actually more effective at preventing chronic buffer blow and the subsequent queuing latency than Cubic, which again relies on filling the queue until something breaks.
Okay, while BBR is certainly optimized for minimal latency, I grant you that, we still have to return to fairness. Cubic's RTT independence for flow growth, as I said, is vital in heterogeneous networks like CDNs. Now, if BBR is estimating RTT to adjust its pacing, how does it ensure equitable sharing when you have two competing BBR flows with vastly different RTTs, especially given its focus on minimizing its own latency and maximizing its own rate?
Right.
And maybe more critically, we can't just ignore the real-world implications of operating in a mixed environment. Studies have already shown that BBR can be, quote, more aggressive and may dominate bandwidth allocation when it's competing directly with cubic flows. So the BBR flow, optimized for maximum delivery, it sees the cautious cubic flow backing off as it's designed to do upon loss detection, and BBR immediately assumes that freed up capacity is available bandwidth. It then potentially starves the cubic flow. A hasty universal deployment could risk a really chaotic transition period where established, stable flows are just perpetually starved by these aggressive BBR flows, potentially destabilizing network performance for the whole ecosystem.
Dominance you're describing, maybe it isn't an algorithm behaving aggressively. Maybe it's just an efficient algorithm exploiting the inefficiency of an outdated one. BBR identifies the true bottleneck bandwidth and it uses it. Cubic backs off, often unnecessarily. Its window reduction is frequently far too large for the actual level of perceived congestion, and it leaves capacity unused. BBR simply fills that available capacity.
You're right that Cubic aims for RTT fairness among flows, but BBR seems to optimize the fundamental connection performance by estimating the minimum RTT. And this optimization prevents those significant retransmission delays that plague Cubic when packets get lost in those high latency paths. Think transatlantic fiber runs or mobile wireless links where random loss is pretty common. The empirical collapse of TCP under high latency and loss, throughput getting effectively killed when latency hits, say, 256 milliseconds, combined with just 3% packet loss, that's the problem BBR is designed to solve.
Okay, but the deployment.
I acknowledge the deployment challenge. Absolutely. Cubic is the established standard. It's baked into every major OS kernel globally. But Cubic's legacy, I'd argue, is rooted in previous network constraints. When the objective today is maximizing real-world throughput, especially for latency-sensitive applications like modern streaming video, which now predominantly uses TCP, by the way, well, maintaining a default that penalizes performance by 70% because of a minor, frankly, inevitable loss rate, that feels like prioritizing historical compatibility over user experience and network efficiency.
But the providers.
And the empirical benefit shown by major content providers, folks like Dropbox and Spotify, they're reporting significant throughput gains and latency reductions in their production environments using BBR. That indicates BBR is ready. We have to transition. Cubic moves bandwidth based on reaction to failure. BBR moves bandwidth based on proactive capacity estimation. That distinction, I think, is the key to scaling the modern internet.
But we still have to manage let's say, the human element of that transition phase. If we acknowledge that BBR dominates existing Cubic flows, then the network administrator faces a potential nightmare scenario where mixed environments suffer severe performance instability. Mandating a switch requires massive global coordination. And furthermore, Cubic's architecture is arguably simpler to integrate into hardware offloads because its window growth function is predictable, it's deterministic. BBR's model-based estimation, while powerful, it definitely introduces complexity that might not be easily scalable or transparently implemented across all hardware platforms. We can't just mandate a switch without fully understanding BBR's long-term impact on the overall network equilibrium, which is precisely what Cubic was designed to maintain, a predictable, if maybe cautious, foundation.
I believe the stability you champion is, perhaps, merely a byproduct of Cubic's inherent slowness in these challenging conditions. BBR represents a leap forward. It moves beyond simple loss-based control to a more intelligent, model-based approach that demonstrably delivers superior performance under the common stresses of loss and latency. The empirical evidence for me is overwhelming. An 8.5% loss penalty for BBR versus a 70.7% loss penalty for Cubic under identical conditions. That's the data point that has to guide our future network standards. It really proves that Cubic's dependency on packet loss as its main congestion signal is fundamentally broken in today's environment.
And I'd conclude that while BBR certainly shows impressive metrics in loss resilience and shear speed, its universal deployment must be approached with considerable caution. Cubic's RTT fairness and its predictable, stable congestion response provide a necessary foundation for interflow competition in a shared network. Discarding that foundation too quickly risks creating instability, where some flows might be starved simply because they adhere to a more cautious, perhaps more network-friendly protocol. We have to ensure that this new efficiency doesn't come at the cost of, let's call it, network democracy.
So it seems we agree that the continued evolution of these congestion control algorithms really highlights a core ongoing tension. The push to maximize individual flow performance and minimize latency on one side versus the critical need to maintain overall network equilibrium and fairness across widely different RTTs on the other.
Exactly. And the challenge really lies in determining whether that old equilibrium, the one Cubic represents, is still adequately serving the needs of the modern high-speed, high-loss, high-latency internet we have today. A complex question indeed.